So hello, welcome everyone to the day 2 of the 2 questions of physics per day series. So we are going to solve these 2 questions from quantum mechanics. First question says that the speed of a bullet with mass 50 gram and the speed of an electron with the mass 9.1 multiplied by 10 to the power minus 28 gram are measured to be same, namely 300 meter per second. So both are traveling with the same speed, but there is uncertainty of 0.01% in the speed. So with the fundamental accuracy, what fundamental accuracy we could locate the position of h if the position is measured simultaneously with the speed in the same experiment. So we know that this is the question which involves measurement of position and velocity. Measurement of position and velocity. So we are going to use Heisenberg's uncertainty principle, which is delta x times delta p, which is greater than or equal to h bar by 2. So here is the basic introduction. Now let us solve. So what we will do, as we have the uncertainty in its speed, which is 0.01%. Okay, so this uncertainty in speed will lead to uncertainty in momentum, magnitude of momentum, and this will provide the uncertainty in magnitude of position, or just position, because position is scalar in the case of one dimensional. So here we are in the one dimensional world. So from the uncertainty principle, the minimum position uncertainty will be given by this particular expression. Okay, so now what we will do, we will just find the momentum uncertainty. You will find the momentum uncertainty. Okay, so it is m times delta v, and delta v is 0.1% of 300. So 0.1% of 300 is 0.03 meter per second. So this is the uncertainty in the momentum, and when you put it here, you will get the uncertainty in the position. So uncertainty in the position of the bullet is 3.52 multiplied by 10 to the power minus 32 meter. And I am skipping the calculation part because you all are allowed to use calculator. Okay, I think you all are smart enough that you will do the calculation part yourself, but we will cover the conceptual part here. Now we will do the same thing for electron. The mass of electron is 9.1 multiplied by 10 to the power minus 31, and the corresponding uncertainty in momentum is 2.73 multiplied by 10 to the power minus 32 kilogram meter per second, and that leads to minimum position uncertainty to be 1.93 millimeter. So we saw that if the mass is around 50 grams, so uncertainty is very less in the position. Why less? Because it is the order of 10 to the power minus 32 meter, so it is very less. But for the electron, it is 1.93 millimeter, so it is somehow great, a lot greater than that value for the bullet. So let us do the physical interpretation for better understanding. So this result shows a dramatic difference in the quantum uncertainty effects. So for bullet it is very less, which is negligible, and for the electron it is significant. Okay, and then we have this simple conclusion here. So you should always write the conclusion. It will help you to fetch better marks. Now let us solve the second question, where we are required to consider an electron whose position is somewhere in an atom of diameter 1 angstrom. So we are required to find what is the uncertainty in the electron's momentum. Okay, and is this consistent with the binding energy of the electron in the atom? Okay, so we should also know the binding energy. Okay, and then we need to find the uncertainty in momentum. So we know that the diameter is 1 angstrom, then uncertainty in the position of the electron will be of the same order, and that is 1 angstrom, and that will help us to find the uncertainty in the electron's momentum. And then we are required to find that is that consistent with the binding energy of the electron, which is in atom. Then you need to imagine an electron to be somewhere in a nucleus of diameter 10 to the power minus 20 minus 12 centimeter. So we have a nucleus which has diameter of 10 to the power minus 12 centimeter. So you are required to find the uncertainty in the electron's momentum now. So we have two uncertainty in position, and that will lead to two different uncertainties in momentum. Then it is asking that is it consistent with the binding energy of the electrons, atoms nuclear constituent, And then the third question is, consider now a neutron or a proton to be in such nucleus. What is the uncertainty in the neutrons or protons momentum? Is this consistent with the binding energy of the nuclear constituent? So we are required to solve these all three questions, A, B, C. In A, we are required to find the electron which is in the atom. In B, we are required to find the data for the electron which is in the nucleus itself. And C, we are required to find the data related to neutron and proton, which are obviously the constituent of nucleus within the nucleus. Okay. So this problem uses Heisenberg's uncertainty principle to estimate the uncertainty in momentum of the particles, which are electron, neutron, and proton. And it is very good question. It will help you to like this one single question is mother of PYQs. Mother of such PYQ. Let us see how, because we are trying to understand the complete atom. So we are going to use this form of Heisenberg's uncertainty principle. So to estimate the momentum, we are required to find the corresponding kinetic energy. So corresponding kinetic energy is given by momentum square upon 2 times mass. So when we compare the kinetic energy with the known binding energies of the atom and nuclei, we get the better information. So electron in atom has the following description, that its position uncertainty is going to be the order of diameter itself. It is so these particles are like so small so that only order matters and magnitude does not matter. Then mass of electron is this and the h bar is this. So from the uncertainty principle, you can find the corresponding uncertainty in momentum, which is delta p. Now if you find the delta p, you can plug that and to find kinetic energy. So kinetic energy is given by 1.53 multiplied by 10 to the power minus 19 joule. Okay, and we are going to convert this into the electronic volt by dividing with this constant. Okay, so this is 0.96 electron volt. So this is of the same order of magnitude as atomic binding energies. We know that atomic binding energy in the first orbit is around 13.6 electron volt for hydrogen atom, and it decreases with this value. N square is the principal quantum number. So for second orbit, it is going to be 13.6 divided by 4 and 13.6 divided by 9 and so on. So we know that okay, this is of the comparable value, the magnitude is comparable, the order is same. So yes, this is consistent with the real observation, actual observation. Now let us try to do the same thing in electron in a nucleus. So if electron is going to be within the nucleus, so this is the whole atom, but this is nucleus. So nucleus is way smaller. That is why earlier we were using 10 to the power minus 10 meter. Now for this nucleus, we have the value 10 to the power minus 12 centimeter, or in meter it is going to be 10 to the power minus 14 meter. Okay. So now when we calculate the momentum uncertainty using the same mathematical computation, we are going to get 5.275 multiplied by 10 to the power minus 21 kilogram per meter second. And thus corresponding kinetic energy in electron volt is going to be very, very large, which is 15.6 million electron volts. So this is very large energy. Okay. This is extremely large compared to the nuclear binding energy. So this is not consistent with the experimental finding. That is why even the Heisenberg's uncertainty principle leads to the same conclusion, that electron cannot be inside the nucleus. Okay, and this has been the PYQ. This has been the PYQ. Now let us find the consistency of Heisenberg's uncertainty principle along with the binding energy when we are calculating the same for the neutron or proton. So we know that neutron and proton are roughly of same mass, not exactly but roughly. So we are going to take the value of 1.6 multiplied by 10 to the power minus 27 kilogram, and this is going to be uncertainty in the position is going to be 10 to the power minus 14, same as the nucleus size, because we know that for our case uncertainty, it is, let me tell you very clearly, uncertainty in anything will be always of the same order whatever you are trying to find. Okay, not the magnitude but definitely the order. you will ignore the magnitude because it won't create much difference in the percentage term. It will be negligible. Okay, let me tell you what negligible. Suppose we have some value 5.375 multiplied by 10 to the power minus 20 meter, and then we have something 9.375 multiplied by 10 to the power minus 20 meter. So these are roughly same in the term of percentage. There is very little difference. So that is why we only focus on the order. This order 10 to the power minus 20, 10 to the power minus 20. So when we calculate the momentum with these values, momentum uncertainty, we are going to get 5.275 multiplied by 10 to the power minus 21 kilogram meter per second, and the corresponding kinetic energy is 8.34 multiplied by 10 to the power minus 15 joule, and in million electron volt it is 52.1 million electron volt. So this is of the same order as of the nuclear binding energies, okay, which is few tens of million electron volt. So it is consistent with protons and neutrons being confined within a nucleus. And here we have conclusion.